Okay, in this lecture, I'm talking about the state feedback, which is about the control system design. So before talking about the state feedback, which is the control system design, I'm going to briefly review what we talked about previously and talk about the difference between the control system analysis and the control system design. So the control system analysis talking about some properties of a linear system given if I already give the input useful t. For example, over here, if I give a linear system, this is a general linear time variance system. So the stability, controllability, observability, they're talking about for certain input, or I could have a certain initial state. Okay, what kind of property can we say in regards to the output of y sub t or x of t? Okay, we talk about stability, controllability, and observability. Okay. Now, the control system design is different from the control system analysis because we're going to focus on giving certain goal of my output y sub t. For example, here, okay, I want to have some output y sub t, which is given, let's say, for example, a step output, and I want my y sub t to be able to track this references. Let's say this is my reference, okay, and my goal is trying to figure out, hey, what ut can we design? Okay, such that we can achieve the goal. Of course, when you start with certain initial value x0, let's say f initial value x0 here, we have a y0 for that initial value. Maybe y initial value is, let's see, my initial value for y is somehow over here. This is my y0. So at least I want to reach this goal as fast as possible, for example. So that's sort of the goal we want to look at. So we want to see how we can design the control input so we can have the desired property of the output y sub t. Okay, most likely we're related to the property we want the yt to track some reference signal. Either the signal is constant or not constant. Okay, so this is sort of a reverse problem of the analysis because we are given the output. We don't know what the input looks like. Well, for the control system analysis, we're given the input, we try to figure out what the output looks like. Okay. So now what's the basic idea of a state feedback? We talk about state. What is a state feedback? So idea of state feedback is as follows. So of course we assume here that my xt, which is a state, is known for all time t. For different time we know the state xt over here. Like here, if I give you this news, I know the xt for a different time. Well, one question is, what if this is not true? Then what if I don't know xt? So there's a way we can also do state observer or state estimator. We can estimate the state. Okay, we'll talk about later on. Now that's the focus of this lecture. Here we assume that xt is known. So the first question is, can we use xt in the design of my ut? The answer is yes, of course, we can use that. For example, I can start a design, hey, if my ut is r sub t minus k of c, this is just some very commonly used control, state feedback control. So this is my reference, and emphasize again, this is my reference, okay, and this is my k time xt, okay. So the main idea for the state feedback is trying to say, hey, I want to compare the difference between the reference or the preferred state r sub t, preferred output st, and try to count the difference between that and my current state times some parameter k, some called control parameter. This is called control parameter k. So this as sort of feedback because I sort of use, if you go back to the, I sort of use my xt to get a feedback to see what's the difference between them. This will help me adjust my control input. Okay. You may also want to ask, can we use yt in the design of use of t? Yes, the answer is yes. We can also use y sub t to do that. Okay. And typically this is a little bit hard to design because compared to the previous one, because the analysis will be harder. Okay. So you can also say, hey, I can design my use of t is st minus y sub t, which is fine. Okay, you can also do that. Okay. Now some of the issues you might encounter if you use this is also called output feedback. There might be some issues we want to address over here. For example, the dimension in compatibility, because typically your state, if I talk about this one, if you remember, I could have an x1.t, which is ax1, a11, x1t plus a12, x2t. I have x2.t is a12, x2, x1t plus a22, this is a12, x2t, and I have my yt, this is x1t plus x2t. As you can see over here, so you typically your output, I could have also has ut and plus ut, whatever I have. So typically your state is high dimension, its dimension is higher than yt, so the yt can provide less information than x, the state x, so the x will be just x1, x2. So the x will provide more information than the y just provides the sum of the two, while the actual state will provide more information. So the dimension incompatibility could be issue. We want to be more careful. The second one is yt. Typically, if yt is given by ct xt plus dt ut, you want to do some change, because here yt also depends on ut, and you cannot do this like a cycle. Ut also depends on yt, and yt also depends on ut. That doesn't work, right? We have to make some changes to it. And even if one or two there's not problem with the first two, typically and yt is comparable to xt, which means if you use a output feedback, it's almost the same as you use a state feedback, because you typically have this form. Okay, so but of course output feedback can be better because the state may not be always available, but output always available. Okay, there's a trade-off between the two different methods. But here our emphasis will be here, the state feedback, this method. Okay, so now let's take a look at what is the basic structure of the state feedback in the control of a linear time invariant system. So here we emphasize on the linear time invariant system, because for linear time invariant system is much harder to analyze. So linear time invariant system, typically what we use as the state feedback. Okay, so for linear time invariant system, here I'm going to get a little bit simplification to reduce last term over here. So for the linear time invariant system, I have x dot t is a times xt plus b times ut, yt is c times xt plus d times ut. So here I drop this term, because if I do have this term, I can make a change. What I do is I change my yt to be y tilde t. So I define y tilde t to be yt minus dut, so I don't have a dependence of yt on ut. Okay, so that's why I can simplify this a little bit without considering this term. Okay, so here's the basic structure if I use the control method. Like here, this is the structure, the overall structure if I use this feedback control, what it looks like. Okay, so structure wise, this is what it looks like. So okay, I'm going to explain this a little more detail so you know what I'm talking about. So this one you do have, so this is what we have. So okay, so this is my input. So assuming that this is my s of t, so starting from here, this is my reference signal. So this is my x of t over here. Okay, so this 1 over s is the integration, which means here I have x dot t over here. X dot t is equal to a times, I should change this one a little bit. So add on this one, a over here. So the x dot t is given by, if you do the plus, is a times x t plus b times ut, okay, which is done over here. And my y is c times xt, yeah, it's given by here. And also my u is given by, this is my u. U is given by the feedback. This is what the feedback coming from. So the black color over here, if I go to emphasize the black area, this over here, this is the standard when we do the analysis. This is a linear time invariant system we typically have, right? If you give the input, you analyze probably is just given by the black one. Well, the state feedback is trying to do this. You're trying to pull this xt, the state, out and get the k. This k is a control parameter. So this is a, you also put a weight on the xt, and then you have a reference signal over here. You try to this kind of rt minus whatever the feedback looks like. This one is called feedback. called state feedback because I'm using the state and feed it back to the control input. That's why I call state feedback. So this will calculate the difference between the reference minus and the k time xt, and you consider this as your input. Okay. Now this is the whole structure for the state feedback of a linear time invariant system. So the red component was added on to the original linear time invariant system. Okay. So here this is use of t is rt time k time xt minus k time xt is called a state feedback control design. So as mentioned earlier, the typical goal here is to design this ut or k. So this is structure to design k. If I use state feedback control design, my goal to let yt track xt. Okay, if I give something, you're going to track over there. It looks something like this. So just if this is a t, this is a let's see, this is my r sub t, something like this. This is r sub t, and y. I want a y. So your y start from a different value. You want a y sort of go back and then gradually approach this y sub t. Essentially, you'll be the same value. So this is my y sub t. So that's the goal. Okay, before talking about how we design this k or the parameter k, I want to talk about a few properties. The first question is, does the state or feedback control change the controllability or observability? Okay, I want to show the reason later on why we have started the problem, the controllability or observability. So the original system, if you look at the original system, the original linear time invariant system is given by this. It's standard form. The after feedback control, so I'm going to have this one. So what I do is I replace this u by the feedback I defined over here. So this is my linear time invariant after the state feedback. Okay, of course here I don't have a u anymore, right? So I have to rewrite this one into a different form with xt dot t, which is a minus bk times xt, because I'm going to combine b times k, combine them, xt move xt over here. I have b times rt. So this one, this I can see this sort of as my control input, right? So I want to see, hey, for this one, for the y will be the same, doesn't change. I want to see, does this one change my controllability or observability of my the difference between the two phases? This is my original one. Okay, this is my new one. I want to check if there's a difference in terms of controllability and observability. Okay, considering here RT is my UT, of course. Right? Okay, so let's take a look at example to see what's the what the end difference is. Okay. So let's start with the example here is linear time invariant system, which is x dot t is 1, 2, 3, 1. This is A matrix time xt plus 0, 1. This is B matrix time ut. Yt is 1, 2. This is C matrix time xt. Okay. So, and of course the feedback, let's say the feedback control loss given by ut time is rt minus 3, 1 xt. So one thing I want to emphasize here, this is my k. So the k doesn't mean it's a scalar. K can be vector, even can be a matrix. Okay, it doesn't mean this is just a scalar value. Okay, so here, because if I don't have it, as we can see from here, so rt here, the xt, why this is the case? Because if you look at this one, rt is dimension, ut here is a scalar. How to determine the dimension of k? First of all, ut has to be a scalar, right? Now, if my ut is rt minus this guy times xt, so this is a scalar, also a scalar over here. Okay, because ut is a scalar, so rt is also a scalar, and xt is 2, right? You have 2 because there are 2. This is based on here, it has to be 2 x1, x2. So your k must be, you cannot be a scalar. If k only a scalar, the dimension doesn't match. You must have k1, k2 over here, okay, to match. So your product will give a scalar, and you can do the scalar minus. Okay, if that's my whatever control input design. Okay, let's see for the original system, what is the controllability of that? The controllability defined by C, we can verify the controllability by computing the controllability matrix, which here for this one is given by B and AB. You don't have any more because the dimension of X is just 2. Okay. If you do the calculation, so B is just 0, 1, and A times B, do the calculation just 2, 1. Okay. If you compute the rank of this guy is 2, because these two columns are linearly independent, so which means that the rank is 2, which is also the dimension of x. X has to be x1, x2, right? So which means this is controllable. Now, okay, if we verify for the other one, okay, if we do the after the state feedback, okay, what we change is y is still the same, but x change. So if we replace here, if you put an a and a b and a k over here, so here this is my k, a and a b and a k over here, so I do the order product, and then I can rewrite this one as this, xt by this. Because note here, this a is different from here a. So this a is a minus bk, so it's different. Also here use a, I mean use a red a. Red a and the black a are different. Okay, red a is equal to the black a minus bk. So b is still the same, c is still the same. So if you look at the control law, the controllability one, if I do c, also the same thing. The difference is a will be different. If you calculate that one, okay, which is c is b and ab. Remember here a is different from this a over here is this new a. So you do this one, so b is still 0, 1, okay, and you do a times b over here, you get 2, 0. So if you can do a rank, because this 2 are also linearly independent, so the rank is 2, which is also equal to the dimension of xt, so this is also controllable, doesn't change, looks like. Now how about observability? If you look at observability, and I can follow the same approach, and observability is computed by C and CA for this case, because this is a two-dimensional. It has the state has there are two states. So you calculate C, and C is C is 1, 2, okay, and CA you compute that is 7, 4. So these two are also linear independent, which means rank of O is 2, equal to dimension of xt. So this is observable. Now, interesting is for the observability for the new one, the new system after state feedback. Now, observability is computed by C and CA. So this A is the red one, okay, not the black one. So if you compute C as this O observability matrix, it turns out this O is equal to 1, 2, and 1, 2. Apparently, this rank they're independent because 1, 1 is 2, 2 is just twice of 1, 1. Okay, this is dependent. So the rank of O is equal to 1, which is less than dimension of xt. So this is not observable. So a general conclusion here is saying that the state feedback does not change controllability, but may affect observability. Okay, this is a general conclusion. So the reason why this is the case, okay, if you look at this one, the reason why the controllability is the same while the observability is not the same, if you take a look at the original system, linear time revision system, I need to check the rank of C, which is given by B, A, B, blah, blah, A, until n minus 1 times B. Well, for the new system after the state feedback, as a state feedback, my rank is given by C prime, is rank of C prime, another controllability matrix, which is a B times A minus BK. So, which means I change the B to A minus BK because the state feedback. So on and so forth. Okay. Now the key approach can use, because I have to do the call a row or call operation. Okay, for example, I can do rewrite this as AB minus BK times B. Well, if I do some linear operation on my columns of B, so I can get a BK and B. Okay, so I do a sum to the second column, the second cluster of the rows or columns, so I can cancel this term, right? Similarly, you do the same stuff. You can continue to cancel out all the terms, which means, yeah, this one essentially the rank of this C prime is the same as the rank C. Okay, if you do these operations, that's why the rank of C is the same. So if the original system is controllable, the new system is also controllable. Okay. However, if you look at observability matrix, is given by C, CA. This is for the original linear time invariant system, C, CA, and CA to the n minus 1. And for the new one, again, I have to change my A into A minus BK. Okay, so we have C time. This first row is C. The second one is C times A minus BK, so on and so forth. Because there's no relationship between C and the B, C and the B, right? No relationship between C and the B, so you cannot cancel out this term. So you should have this one. So that's why the observability could change. So the rank of this guy and rank of this guy, generally they're not equal. They could equal, but they may not be equal. That's why the observability could change. Okay. The question number 2 is, how about stability? Okay, we talk about the controllability and observability, right? How about stability part? Does the state feedback change the stability of the original system? Okay, we do the same analysis. Okay, let's say original system given by x dot t is a times xt plus b ut y ct. This is the original linear time reverse system. If I use the state feedback, which means I'm going to use ut is r sub t minus kxt. Okay, this is my state feedback. Okay, so if I substitute this ut by this one, so I can rewrite my system here as xt, which is equal to a minus bk times xt plus brt, and y is still the same. So as I mentioned before, the stability doesn't matter if it's marginal stability, asymptotic stability, or BIBO stability. They are all related to the eigenvalues of some matrix. So for the original matrix, eigenvalues of A, pretty important, or the eigenvalue of A minus BK. If it is this is the original one, I have to check the eigenvalue of A. That's pretty important role. And also A minus BK, right? So here, all for the feedback one. Well, because we change, if we introduce this BK, so we definitely change this matrix, right, from A to A minus BK. So our observation here is the eigenvalues of A and minus BK can be different from the eigenvalues of A. That's why the stability could change, okay? Because if I do A minus something, my eigenvalue could be different. So which means the eigens of A can be completely different from the eigens of A minus BK. So controllability could change, okay? So the next question is, can we randomly assign the eigenvalue of A minus BK? Because I want to check the stability value. If you wanted to make a stability, if you still remember, so stability says, so for marginal stability, asymptotic stability, and BIBO stability, so the typical requirement, I want eigens of my A, or I want an eigen of A minus BK, if you consider the feedback system, right, to have negative real parts. So that's typically. So my goal is, can we as a random? My goal is to want to make sure that the eigenvalue have negative, because that can guarantee the marginal stability, asymptotic stability, BIBO stability. Okay, my question is, can we random assign? Can we random assign the eigenvalue of A minus B? If that's possible, which means we can assign the eigenvalue of A minus to be negative, have negative real parts, which is great. Okay, the answer is yes, and some conditions. If A and B is controllable, which is the same as if, equivalent say if my original linear time invariant system, if the star here is controllable. So as long as it's controllable, I can randomly assign this eigenvalue, which means great, because I can always guarantee the system is stable. Even if my original system is not stable, by its design K in a proper way, I can always guarantee that for this system, for the system after state feedback, is always stable, always marginal stable, asymptotic or BIBO stable, which is great. Okay, so next time, in the next video, I won't have time to talk about how we compute the design K. So next video we'll talk about how we assign the value eigenvalue of A minus BK. In other words, how to design my control parameter K.